1 WS. Now delta E delta T is roughly equal to h bar, so delta E delta T is h bar, okay, and so this delta T then is 1 over WS, so that you can bring the WS over the other side, so you'll get h bar WS, right? And that's so the uncertainty of the energy of the photon being released is of this order, h bar omega s. So what is this omega s? Well, it's the rate of spontaneous transition. Okay, so you get this kind of thing. Now, this sort of phenomena is occurs in when you're talking about spectra. When you heat up substances, they radiate at a characteristic set of frequencies. Now, the actual spectral lines, they actually have a width due to this kind of phenomena. So if there's an uncertainty in the energy due to this kind of thing, then there'll be a spread in the frequencies of the spectral lines. Okay, so and that spread in the uncertainty of the energy is inversely proportional to tau, and tau is the lifetime of the excited state. How long does it last, roughly? Okay, so that means as tau goes up, let's see, as tau goes up, then let's see, intuitively, so as it's more stable, as tau goes up, so the spontaneous rate goes down, right? Because it's more stable, it goes down, and that means this here goes down, right? This is the rate, and hence the delta E goes down, and so the uncertainty in the energy of the spectral lines goes down. In other words, they get sharper. They get less spread out. The spectral lines are sharper, less spread out, which is what you'd expect. Okay. Now, there's something similar occurs in classical electrodynamics. Okay. If your simple harmonic oscillator decays with radiative emission, so if it's oscillating and it's shooting off particles, photons, then its amplitude, it's a simple harmonic oscillator, right? So its amplitude, it'll lose energy because it's shooting off photons, and the amplitude will die off exponentially, and according to this kind of formula, right? Where your T here is the lifetime of your excited state. So there's something familiar here in classical mechanics as this kind of phenomenon in spectral analysis when you look at the spectra in quantum mechanics. Now, a lot of stuff here just thrown at you. You're not this is me saying, you're not expected to understand it all. It's more sort of give you a taste of what you could learn in quantum mechanics at higher levels. Right, well, I'll stop there formally in terms of the theory session of this whole course, and just make some closing remarks. I hope. Well, see, I don't know what your mix of needs are. I can imagine there's quite a spectrum of audience. Some of you may just be curious to study undergrad physics, quantum mechanics, and that's fine. Some of you may plan to go on. You're more ambitious and you want to study graduate level physics, in that case, then undergrad quantum mechanics absolutely essential, give you the basis, so you can go on to study things like quantum field theory, more advanced quantum mechanics, master's level quantum mechanics course, where we'll meet a lot of this stuff, but at much greater detail, of course, and actually derive it instead of it having thrown at us. QED, quantum electrodynamics, then second year undergrad, master's level, QCD, quantum chromodynamics, the quantum field theory of quarks and gluons, the strong force. So there's plenty of quantum mechanics to come, and so what you've done in these 200 plus clips is just the tip of the iceberg, right? It's just the beginning. But I hope you've enjoyed it. There have been frustrations, I dare say, on your part, certainly on mine. My personal preference, I like understanding stuff. I like having things presented to me in textbooks or in a speech or wherever that are clear, so that you can deduce from step to step how things work and where things came from and so on. That has not always been the case in this text, but to be fair to the authors, expecting such is almost impossible, right? There's, especially in the later lectures, they're trying to give you a feel, an overview of what quantum mechanics is about, and so a lot of the stuff is just stated rather than derived. I mean, attempts have been made to derive it, but often with so much material between the lines that you just feel lost. You know, where did that come from? So if you've been feeling like that lately, then that's not surprising. If it really bugs you and you really want to understand, then follow me at higher level courses. Okay? So I hope you have enjoyed it, and well, there's still the theory session for this lecture before this course is actually finished. But I have a backlog, like I've been saying. I have a backlog of problem-solving sessions to film, which I haven't done about half the course's worth, in fact, and probably a bit more. So I still have quite a bit of work to do on that score. But I think I'll mix it with some theory of computation as well. I'll probably switch back and forth to just for a change of pace on my part, to do some computer theory, because this whole series, deGarisMPC, is pure math. That was the first course on group theory, junior senior level. Second course, this one on quantum mechanics at senior level, and the third one will be on computer theory, strictly speaking theory of computation, is at senior M1, first year masters level. So I will start doing that as well as finishing off the theory, the problem solving sessions for this second course on quantum mechanics. So I hope to see you in the third course on computer theory, which will be on what you can compute and cannot compute, so computability. We'll actually prove a lot of math type theorems, that some things just are mathematically provable to be impossible to compute, right? Which is fascinating concept. So there are things that computers cannot do and will never do. Impossibility proofs. What else? Computer languages in the abstract. Turing machines. Notions of complexity, like why calculating some things in computing takes huge amounts of time. Why is the problem so much more difficult than other problems? And that leads into the notion of complexity, like the number of steps, for example, involved in performing a calculation, and related to that, like the amount of memory needed. So you talk about time complexity and space complexity and that kind of thing. Now, this text that I'll be using, SIPSA, it starts off pretty easily, so you get the false impression that it's a pretty easy course. Well, that's because it's starting off at senior level, even junior level, in the first chapter or two. But towards the end of it, it's getting quite hard. It ends up definitely in one level, because it's effectively, it becomes pure mathematics. Pure mathematics in the context of computer science theory. You know, what can you compute and not compute, and how do you compare various problems in terms of their complexity levels and all that stuff. You know, the math. If you like pure math, you will like this course because it is very pure mathsy. Okay, ciao.